Hello everyone. In this unit, I am going to discuss about biasing and stability, which are the most important factors connected with an amplifiers, which comes under Unit 2 of analog electronic circuits. Unit 2 B.JT biasing and amplifiers, analog electronic circuits. So let's see what are the contents we are going to cover. So in this unit, we are going to discuss about DC load line, stability factor, voltage divider bias for BJT. So let's start with the DC load line. So DC load line, the name itself indicates it's a DC characteristics. It's one of the important factor to be considered when we design an amplifier. So the DC, the first point, read out the first point. The DC operation of a transistor circuit can be described using a DC load line. So DC operation of a transistor circuit means, as I already explained in the previous videos, when we want to work a transistor as an amplifier, it should be properly biased. Biased means nothing but an biasing is nothing but an applying proper DC voltages to the amplifier so that without applying a signal, some collector current flows. So biasing is necessary to make the transistor to operate in an active region. So when you do the biasing, we are going to apply the DC voltages. So these DC voltages we get either by using a resistor, capacitor, or by applying a DC voltage. So when you apply the DC voltages and the DC operation of that transistor can be understood with the help of a DC load line. So what is DC load line basically? It's a line, straight line drawn on the output characteristics curves from the cutoff point to saturation point. In the transistor output characteristics, that is always we talk about the CE mode. CE mode, the output characteristics is collector emitter voltage versus collector current. So when you draw the output characteristics, in that characteristics, when you draw a line between cutoff point to saturation point. Cutoff point, already I have explained, it's a point, okay, where the base current and collector current are zero. So cutoff means the transistor will be off, no current flows. So what happens is in a cutoff current, no base current and no collector current. Then one more point is saturation point. So in a saturation point, the maximum collector current flows. So in this case, the maximum capacity of that amplifier, which that collector current can flow, that much current flows. So it's totally on state. So what we say that collector to emitter voltage is zero and IC, the collector current is equal to saturation current on the y-axis. So we will see the graphical representation of that. Before going to graphical, so DC load line when we draw, as I said, the transistor is given a bias. What is bias? It's nothing but an applying a DC voltages. So here the DC voltage is VBB, which is applied between the base, and VCC, which is applied between the collector. And when the transistor is given the bias and no signal is applied, we have not applied the input signal, and when we draw the load line under this condition, it's called as a DC condition. Understand once again, when you apply a signal, it becomes an AC signal. So before applying the signal, when we use a transistor as an amplifier, we are going to apply the biasing voltages. The biasing voltages are VBB and VCC. One voltage is applied across the input circuit, across the base emitter. One more is applied across the collector emitter. And this is called as a bias. So when you draw the load line under this DC condition, that is no application of the signal is done or the signal is absent, then that condition is called as a DC condition. And the line drawn under this condition is called as a DC load line. So how to draw? This is very important. So in this diagram, you can see the transistor circuit. So in this circuit, we have applied the bias voltages VBB and VCC. no signal is applied, and this is the output characteristics. So in the output characteristics, it's nothing but it's between collector emitter voltage and collector current. And this is the DC load line, blue color line, which is drawn, which joins the point, cutoff point and saturation point. So how to get these points? So in this diagram, if you consider the output circuit, because the DC load line is drawn on the output characteristics of a transistor. So consider this output circuit, so which has an current flowing, collector current is flowing, VCC is the bias voltage, and RC is the load resistor where we take the output. So the collector emitter voltage VCE is given by VCC minus IC into RC. That is the current flowing through the resistor. This is the first equation. See here, VCE, that is collector emitter voltage, is given by the the bias voltage VCC minus IC into RC. So this is a linear equation. This is the first equation, which is we have taken from the output circuit of this transistor without applying the signal. So to add the load line or to draw the load line on the output characteristics, we need 2 points. So how to get these 2 points? To find the 2 endpoints on a straight line, for a straight line to draw, that is a DC load line, first makes IC equal to 0. So because we wanted 2 points, one is a cutoff point where the collector current is 0, and one is a saturation point where the collector current is maximum. So to get the first point, that is a cutoff point, assume that the collector current is 0. So when you make the collector current 0, what we get is collector emitter voltage is equal to the supply voltage. This is the first point, cutoff point, where VCE is equal to VCC. This is the first coordinate. To find out the next coordinate, to draw the DC load line, what you make is VCC, you make it a 0. So VCC, when you make it a 0, the second point is, sorry, VCE is made 0, that is collector emitter voltage is 0. So what happens? 0 is equal to VCC minus IC into RC. When you simplify, the collector current is nothing but an VCC divided by RC. This gives the coordination of the second point where the maximum collector current flows. So the 2 endpoints so obtained are joined, and this forms a DC load line. So basically, a DC load line represents the DC condition of a transistor when no signal is applied. And this load line is drawn by joining the 2 points. One is a cutoff point where the collector current is 0, and one is a saturation point where the maximum collector current flows. So the load line, when you draw it, it intersects here. The load line intersects the output characteristics at various points corresponding to different IB. So the output characteristics of the transistor, we can draw the load line, DC load line. So DC load line is nothing but it's going to represent graphically the DC bias condition of an transistor amplifier. So to draw the DC load line, you have to join the cutoff point and saturation point in the output characteristics of an C amplifier transistor. So to get that, we have considered the output circuit, and the equation was VC equal to VCC minus ICRC. This is the equation. In that, to get the first point, IC is made 0, where we get VC equal to VCC. To get the second point, VC is made 0, so we get the maximum collector current flowing. So when you join this, we get a DC load line. So DC load line basically represents the DC voltage condition of a transistor. Okay, the next topic is a thermal runaway. It's also very important when we consider a transistor to work as an amplifier. So thermal means the name is temperature. So in the previous sessions, we have studied the Q point or operating point. The operating point is nothing but an, when we bias the transistor, we get an zero signal, that is without applying the signal, some collector current flows and some collector emitter voltage exists. So the zero signal conditions of IC and VCE is known as an Q point. So once Q point is decided, it should be fixed. It should not move whenever any parameter changes. But what happens in a transistor is the collector current, here it is represented, the collector current in a transistor changes rapidly and tends to shift Q point. Why the collector current changes is, the collector current is dependent on a temperature changes. So when you operate a transistor for a longer time, it may heat up, and when temperature changes, the collector changes. Or suppose the transistor parameters are there, one is a beta. Beta is called as a current gain. Okay, this is nothing but an output current divided by the input current. If beta changes or temperature changes, the collector current changes. Okay, and VBE, the base emitter voltage, is also related to the collector current. Why? Because when base emitter voltage changes, the base current changes. Base current is directly proportional to the collector current. So if beta changes or the base emitter voltage changes, or one more reason, temperature changes, the collector current changes. So the collector leakage current is ICBO is dependent on temperature. So the flow of, when collector current changes, this produces a heat. So when collector current changes, it produces the heat, and this heat in turn raises the transistor temperature, and which in turn increases the collector leakage current. It's called as a ICBO. The leakage current is because of the minority carriers. So when the leakage current increases, it's a cumulative, means within a second, the collector current may become very large and the leakage current increases, and this causes the transistor to burn out. So this may destroy the transistor, and this is known as a thermal runaway. So the name is thermal is nothing but because of the temperature change. The temperature in turn, which is the leakage current is dependent on a temperature. So if the transistor collector current changes because of the changes in parameter of beta and VBE, which in turn increases the heat within the transistor. When heat increases, the leakage current increases, which is dependent on temperature. So leakage current is cumulative. Within a fraction of second, a huge amount of current flows, and this may cause the burning of a transistor or destruction of a transistor. So this is called as a thermal runaway. So always we have to design a transistor amplifier circuit so that it avoids the thermal runaway. And if thermal runaway is avoided, then operating point is also fixed. So basically, the thermal runaway is nothing but the collector leakage current, which is dependent on temperature. So the flow of collector current produces the heat in a transistor. This heat increases the temperature of a transistor, and the collector current increases. And this effect is cumulative. Within a fraction of second, the collector current may become very large, causing the transistor to burn out. So this self-destruction of an unstabilized transistor is known as thermal runaway. So to avoid that, we have to do the proper biasing. And when we do the biasing, the operating point will be fixed. So how to do the biasing? What are the different methods of biasing? We will go with the next unit topic. So as I said, the collector current is dependent on a temperature, the transistor parameter beta, and the base emitter voltage. So this variation in collector current is measured by the stability factor. That is, stability is nothing but how stable the collector current is there. So the stability factor may be defined as rate of change of collector current with respect to the reverse saturation current. So as I said, when collector current changes, the leakage current change, it produces the heat. This heat in turn changes the ICBO, that is reverse saturation current. So the stability factor is nothing but a rate of change of collector current with respect to the reverse saturation current, keeping beta and IB constant. Okay, so what is the change in collector current with respect to the change in reverse saturation current is measured by the stability factor. Okay, so stability factor indicates the change in collector current due to the change in collector leakage current. So to understand in a better way, for example, the stability factor of 50 of a circuit means, so suppose one amplifier circuit is there, in that we mentioned that the stability factor is 50. So it means that the collector current changes 50 times as much as change in CBO. Suppose 1 microampere of reverse saturation current changes, 50 times of that the collector current changes. So when large collector current flows, it's a destructive and the transistor may blow out. That's called as a thermal runaway. So this thermal runaway or a change in collector current because of change in reverse saturation current is measured by the stability factor. It is defined as rate of change of collector current with respect to the reverse saturation current. This plays a very important role in forming a transistor amplifier. Next, so we discussed in the first one DC load line, the biasing, how to draw the DC load line in this unit. Then now we discussed about the stability factor. Stability factor is nothing but an in order to work a transistor as an amplifier, the Q point must be fixed. But if IC changes, the Q point also changes. This is because the temperature changes, the reverse saturation current changes. So in order to provide a better stability, that is the Q point should not move. For that sake, and to avoid the thermal runaway, we are going for a transistor biasing. So for a transistor to function properly as an amplifier, an external supply voltage must be applied to produce the desired collector current. So for that biasing, we do the bias is defined as a controlled voltage or current, and transistor must be biased correctly to produce the desired circuit voltages and current. Why we go for a biasing? To get the stable Q point or a operating point. So stable Q point means if any variation of a transistor parameter occurs, the Q point should not vary and transistor should properly function all the time. This is done with the help of an biasing. That is, if you provide a proper biasing, the thermal runaway will not occur and stability factor will be good. So there are many methods of biasing are there. The three common used methods of biasing are base bias, where through the bias using a resistor we are going to provide the biasing voltage. The second one is an voltage divider bias, where we use the two resistors which we are going to study in the next slide. Next one is an emitter bias. So let's go with an voltage divider bias for B.JT. So this is the most widely used method to provide the biasing to the transistor amplifier circuit. So why it's most usually used? In this biasing configurations, it's very simple. The biasing, when we do the voltage divider biasing, what happens is the transistor circuit is made independent of changes in beta. Okay, when beta changes, the biasing voltage will not change and collector current will not change. Beta, as the biasing voltages are set at the transistor base, emitter and collector terminals are not dependent on external circuit values. External circuit values means it is the biasing voltages are not dependent on a beta. Okay, so in order to, why the name voltage divider? It has come from the configuration that it uses two resistors, R1 and R2, from the supply voltage, and it divides the voltage across R1 and R2. And R1 R2 are connected series, and at the center of R1 and R2, a divider network across the supply with their center point junction is connected to the base terminal. So the voltage is divided across R1 and R2. That's why the name voltage divider bias. It's also called as a self-bias method, and it's the most commonly and very important method of biasing. Why it's very important is, in this, the biasing is independent of the transistor parameters as a beta. So if beta changes, the biasing is not going to change. So let us analyze how the biasing circuit works. So this is the circuit of a voltage divider biasing. So in this is a common emitter transistor. Three resistors are used, R1, R2 and RE. These are going to provide the biasing voltage to the transistor. So R1 and R2 are connected in series with the supply voltage. The center of R1 is in turn connected to the base. Okay, so the voltage is divided across R1 and R2. That's why the name voltage divider has come. So the voltage drop across R2, that is nothing but an base emitter voltage, always keeps the base emitter junction forward bias, and the voltage drop across RE provides a stabilization or a stability factor. We studied in the previous session, stability factor is nothing but an ratio of change of collector current with respect to the reverse saturation current. So this RE provides, if the collector current changes, the base emitter voltage will change and it provides the stabilization. So biasing is provided by R1, R2 and RE provides the stabilization. So circuit analysis. So what I said is, in this circuit, VCC is applied through R1 and R2, and at the center of R1, R2, it is connected to base. So the base voltage is nothing but the voltage developed across the resistor R2. So VB, that is the base voltage, is nothing but an voltage developed across R2, and that is nothing but an voltage divider rule. The supply voltage is divided across R1, R2. So VCC divided by R1 plus R2, and the voltage and the resistance at which the output is taken. So the voltage across the base terminal is VCC divided by R1 plus R2 into R2. Now the emitter voltage, that is nothing but an voltage across VER. If you take the emitter voltage, it is developed across the resistance RE. So VE, that is emitter voltage, is given by VB, the base voltage, minus VBE. Okay, so this is the base voltage is nothing but an voltage across R2 and VBE. So this is the closed circuit. VE equal to VB minus VBE. Then the current flowing through the emitter is nothing but an, you have studied the Ohm's law, I equal to V by R. So the emitter current flows through the RE. So IE equal to VE by RE. And always in a transistor, the collector current is almost equal to IE. Then the collector voltage VC, which is taken across the resistive terminal RC, is given by, this is the collector circuit, VCC minus IC into RC. The collector emitter voltage, that is, this also plays a very important role, VCE, is given by VC minus VE. So in this circuit, one of the important thing is, if IC changes, so we will see here, if IC changes, if collector current increases due to change in temperature or change in beta, okay, so sometimes the transistor is working, and when it is working, the collector current may increase or decrease. So we take the condition collector current increases, due to change in temperature. So temperature changes and collector current increases, or the beta changes and collector current increases. So what happens? The emitter current also increases, because we know that collector current and emitter current are related. So when emitter current increases, we have connected the resistor across the emitter terminal. So naturally, when IE increases, the voltage drop across RE increases. When RE increases in the base circuit, we have noted down that VB minus VBE equal to collector voltage, VCs. So when RE increases, this in turn reduces the voltage between base and emitter. See here, if the collector current increases, the emitter current also increases. If emitter current increases, the voltage drop across RE increases. If voltage drop across emitter terminal increases, the voltage across base emitter, this is the input circuit, that is decreases. So when base emitter voltage decreases, the base voltage decreases, the base current decreases. So it's a current control device. If base current, the collector current is dependent on the base current. So what happens when base current decreases, the collector current reduces. So what we are going to say is, we can say that there exists a negative feedback in emitter bias circuit. So this reduction in collector current compensate for the original change in IC. Why we are using a voltage divider biasing is in order to give a proper stability to the amplifier circuit. Proper stability means if IC changes because of change in temperature or because of change in beta, the operating point should not change. So this will not happen if we use a voltage divider method of biasing, where we use a two resistors which is connected across the supply voltage. So how it compensates is, if the collector changes, current changes due to temperature or due to the beta, the emitter current increases, which in turn increases the voltage drop across RE. This makes the base emitter voltage reduction. So when the voltage in the input circuit reduces, base current reduces. When base current reduces, the collector current reduces. So there is a feedback, what we can say. It's a negative feedback exists in emitter bias. So negative feedback means if collector current increases, base current decreases. It's called as a negative feedback. So this reduction in collector current compensate for the original change in IC. So there will not be any change in a IC even though the temperature changes or the beta changes. So this is why, that's why we go for an voltage divider method of biasing in an amplifier. So this completes the session 2, where we studied the DC load line, we studied the stability factor, and we studied the voltage divider method of biasing. Let's solve some of the questions on multiple choice questions. So the first question is, to draw a DC load line of a transistor, the following points are joined. What are the two following points? The first option is cutoff and saturation. Second is active and cutoff. Third is active and saturation. Fourth is none of the above. So see, the DC condition represents without a signal. Without a signal, we are going to draw the DC load line. So when we apply a proper DC voltages to the transistor, it's called as a biasing. When we do the biasing, the DC load line can be drawn. So it joins the two endpoints. So active region lies in the middle region. Endpoints means, so these two actives will not come. So the answer will be cutoff and saturation. Second one, when temperature changes, the output is shifted due to. So in thermal runaway, we studied that when IC changes, it produces the, when large amount of collector current flows, it produces the heat. So that's why temperature ranges. When temperature changes, what changes is change in VCC. No, it's a supply voltage. Change in ICBO. This is called as a reverse saturation current. So when temperature changes, this change will occur And because of this change, the output will be shifted. So the answer for second is an change in ICVO. That is reverse saturation current. Next, question number 3. The circuit that provides best stabilization of operating point. What is stabilization? Change in IC because of change in reverse saturation current. That is nothing but a stabilization. In order to provide a stabilization, we go for an biasing. So previously we studied the most important and widely used method of biasing. That is nothing but an voltage divider bias. So the circuit that provides best stabilization of operating point is voltage divider bias. Fourth question, the stabilization of operating point in potential divider method is provided by. So as I said, we use 3 resistors in voltage divider method, R1, R2 and RE. We use 2 resistors, 3 resistors. R1, R2 makes the base emitter forward bias, whereas RE, the voltage across RE gives the negative feedback and change in IC will be controlled. So that is nothing but change in IC versus change in reverse saturation current is nothing but a stabilization. So the stabilization of operating point in potential divider method is provided by RE consideration. Next, the potential divider biasing is used in amplifiers. Make the operating point independent of beta. Limit the input AC signal. No. To reduce the cost. No. To reduce DC base current. No. So the answer will be make the operating point independent of beta. So even beta changes, the bias voltage will not change. So for that sake, we use a potential divider method of biasing. The ideal value of stability factor. What is stability factor? The change in IC with respect to change in ICVO. If reverse saturation current, that is the ideal value of stability should be 1. Okay, it's not 100, 200 or more than 200. It should be 1. Next is 7th question. Thermal runaway occurs when collector is reverse bias, transistor is not biased, emitter is forward bias, junction capacitance is high. So we studied voltage divider bias. In that clearly I have explained the thermal runaway is nothing but an it's a sudden rise in collector current so that the temperature increases, and this in turn increases the reverse saturation current and the transistor may destroy. That's called as a thermal runaway. So to avoid thermal runaway, we go for an biasing. So thermal runaway occurs when transistor is not biased. So answer is B. So this completes the second session. So in this we covered DC load line, a line drawn on the output characteristic curve of a transistor between cutoff and saturation point. We studied about the stability factor. It's a ratio of change in collector current with respect to collector reverse saturation current. Okay, then we studied about a biasing method, that is voltage divider method of biasing, which is the most commonly used and which has the many advantages. That is when we do the biasing using voltage divider method, the transistor circuit will be, that is the collector current is independent of beta and temperature changes. So always we go with an voltage divider method of biasing. Hope you have understood the topics in a better way. Thank you.